Data Science Central webinar. I'd like to first of all thank TIBCO Spotfire for sponsoring today's event. We're very excited to have them as a supporter of the Data Science Central community, and we are honored to have them sponsoring our event today. I would also like to take this opportunity to mention and show our appreciation for some of our other recent sponsors, including Tableau, Pivotal, LavaStorm, Hortonworks, and Splunk, to name just a few. These past webinars are available on demand at datasciencecentral.com, and if you have not had the opportunity to view them, I would encourage you to take a look, as they do provide some very good perspective and insight into our industry specific to the discussion. Today's webinar is entitled Beyond Simple Visualizations, Adventures in Interactive Model Building. Before we begin, I'd like to briefly review the format of today's webinar. Today's event will be 1 hour long. We have a single sponsor that we have a single panelist that I will introduce to all of you in just a moment. We should have about 15 minutes of Q&A following the presentation, and this event is being taped and will be available on demand at datasciencecentral.com within a few days following. I would also like to encourage our attendees to provide questions directly to me throughout the presentation. I will be reviewing them and presenting them on your behalf following the presentation with the time remaining. My name is Tim Madison, and I am one of the co-founders of Data Science Central, and I will be your host for today's event. I'm very pleased to introduce our panelist, Eric Novick of TIBCO Spotfire. Eric is a data scientist with TIBCO Spotfire focusing on financial services. He brings extensive experience in this field, having worked exploratory data analysis with a special emphasis on model building. You will learn the advantages of interactively fitting and validating models, using graphical methods for model validation and tuning, using simulations to evaluate model fit, and assessing predicting accuracy with ROC curves. So Eric, again, thank you for joining us today. We're happy to have you and looking forward to your presentation. I'm going to turn over the presentation to you, and you can begin as soon as you're ready.
Thanks, Tim. I've just shared the screen, and hoping it would come through shortly.
Play.
Great. Okay, so I assume it's coming through fine?
It is. It looks fine.
Good. So I'll get started. Thank you very much, Tim, for the introduction, and thank you everyone for joining me this morning, afternoon, or evening, wherever you may be. It's an honor to speak to all of you. I hope you find this useful, if not a little entertaining. And I certainly encourage you to ask questions, submit them if we get to them during or after presentation. So we try to answer them later on. So just to set the stage for this discussion, this is not a talk, about how sort of the end user app looks. This is more of the talk about how the sausage is made. And so, we'll explore some of the ways to work with the tool to look at the data to build some models. So get a little bit messy, but in a sort of a fun way. And I think that it's kind of an exciting time to be in data science today, because we're evolving from looking at a lot of static graphs, and we're advancing into this area where everything is becoming dynamic. And I think a lot of advantage can be gained from this interactive analysis, not just by end users, but by the modelers and by the data scientists, without removing the scripting component out of them. So the idea is not to eliminate scripting. The idea is to enable it with a dynamic process. So with that in mind, let me get going. So the problem that in a very generic terms, that we have data that is sitting in a variety of different data sources, right? In SQL databases, social media streams, and Excel, and inside of these little yellow elephants that sometimes referred to as Hadoop clusters. And what we want to do is we want to sort of uncover the structure in this data, and we want to ask some questions, right? And some of the questions that we ask is, hey, should I make a trade or not? Should I extend credit to a potential customer? What are next year's sales are going to be? Or, for instance, should I quit smoking? What would happen to me if I did smoke? So the kind of problems that I'm going to be talking about today are mostly in this area, in these first three categories, which is generally in the predictive world. The inference world is a stricter world, requires some strong assumptions and a sampling method that I'm not going to be discussing today. So that's kind of a scoping statement. So what is generally the path that we take on understanding our models and deploying these models, right? So there's a data acquisition step. There's data munging, right? Reshaping, reformatting data. And then there is exploratory analysis, model building, and model validation. So these first two are actually really hard problems, and a lot of tools exist for doing that. I'm not going to be covering them today, and instead I'm going to be focusing more on the exploratory, on model building, and on the validation piece. Right, so that's basically it's going to be the focus, but we keeping in mind that some work has been done already in acquiring the data, bringing it in, and putting it in the form that it's actually suitable for analysis. So the question that is, I think, a reasonable to ask is like, what does it take, and how, where can we sort of speed this up? Where can we be more effective? And so if you look at it from a standpoint of, hey, we took a sample of some data, maybe we took the entire data set, we looked at some relationship, then we fit some kind of a model to data. Then we ask a question like, is this model good enough? And that's a hard question, because we know that this is not physics and social sciences and finance, economics, and behavioral data. There are no natural laws, so we're not trying to uncover those. So models are wrong. The question is, are they good enough for what we're trying to do? And there I'll offer some suggestions, and maybe what are some of the things we want to look at, depending on the kind of questions that we ask all of these data. And so we iterate this loop, right? We say, hey, no, the model is not good enough. Let's try it again. Let's try it again. Let's try it again. And finally, hey, it's good enough for our purpose. Then we need to do some optimization. Perhaps we put it in some kind of production environment. And there we've made some advances from where we used to be some years ago, where you needed specialized programmers to create an optimized version of code. So we can often work in our favorite scripting environments And I'll show one that we've created and show some sort of performance advantages there. And then finally, once we deploy the code into production, every software engineer out there, what they do once the code is in is they pray. They pray that the software doesn't break, and at the very least they pray that if it does break, it couldn't be traced to them. So I'm not going to help you solve that problem, but hopefully what we could talk about is how to get this loop and how to optimize this loop a bit and become better at iterating. So the very first is sort of understanding relationships. And now it's not understanding romantic relationship. This is not that kind of talk. So we're talking about understanding relationships in data, right? So these types of relationships, for instance, this is a heat map of a distance measure in various DNA probe sets. So we'd like to make comparisons within these data. And in order to help with that task, a couple of things are worth noting. My old statistics teacher always told me that statistics is about comparisons. That's really what it's about, and we need to keep that in mind when we're exploring data, when we're looking at models, how we can present them so that comparisons are made easy. And speaking of that, a pie chart is not a great comparisons tool, right? Because it's hard to tell once there's a lot of slices how they relate to each other, unless it's this kind of pie chart. That kind of pie chart is pretty good indeed. Okay, so we're going to look at these three avenues of graphical exploration that I'll go through. One is looking at the features themselves of input data exploration. And the other two will deal with direct model and model performance exploration. And I will sort of note what are some of the differences between the two. And again, we'll keep in mind that what we're really after are making meaningful comparisons. There was an article published in Wired some time ago, this end of theory, and they suggested that today we don't really need to understand the model, right? We can throw, and they use that example of Google, you can throw large computational power against the problem and then have it make predictions. Who cares what goes into the model? And there's some truth to that. In some problems, I tend to think that there is some value in actually understanding what the model is doing and why it's doing it. And the reason is that at the very least, in the world, even in the world of predictions, we'd like to understand when the predictions stop working. Like, why did they stop working, right? So here's two different ways in which we can look at the models, right? Direct is sort of exploring the parts of the engine and looking at, the components to see how good they are. And the other is just driving the car, right? So in our context, maybe looking at size and error of coefficients, model fit characteristics, and so on would be
I mean, it's catching up now.
I see.
So there seems to be
quite a bit of delay.
Yeah, there's some kind of delay. Some of the people on the call are not experiencing the problem, so it may just be me. So why don't you continue on? So
okay.
So it may just be my connection. So why don't you continue? And if the audience is letting me know if there's issues, so my apology for stopping the flow. Please continue.
That's okay. No problem. So we mentioned this. This area where we try to explore the input variables. We kind of want to do that quickly, and that's sort of the first demonstration that I'd like to do. Here we're looking at a data set that I'll introduce in a moment, which is a financial series data set that has returns from different exchange-traded funds. And the point of it is we're trying to see how these distributions relate to each other, and the wider ones tend to be more risky. Is basically the idea. So I am now going to do this first demo, and maybe you could, Tim, you can tell me when the demo screen is available. So I'm going to stop the PowerPoint. And I'm going to go into Spotfire.
That's looking fine.
It's looking fine. I'm up
Yep.
on the application. Okay, great.
Yes, I think you're good.
All right, terrific. Okay, so this is a data set that contains a time series for about 5 years and returns of 50 highly liquid ETFs. So what we're trying to do here is do like a very quick exploration of these returns. So I'm just going to do a new visualization here. Pick a bar chart, change the axis to returns, and here it allows me to change the number of bins of this histogram on the fly. So here it is. Now I'm looking at overall returns or market returns for the entire data set. So what I'd like to do is to trellis these and look at the individual ones. So I'll just kind of throw that on to the trellis pane, and here we go, trellis them. I will now adjust the axes so that we can see this a little clearer. So I'll allow for multiple axes. Okay, and then perhaps color it by category, which is kind of an industry classification. And we're done, right? So now I can sort of explore and look at these distributions. Say, you know what? The indices that are in the same industry, for instance, the brown ones tend for, you know, X number of tickers as well. We will come back to this data set later, but what I wanted to show you now is I'll introduce you to another data set that I have and another type of visualization that I like to do. And this one will explore a relationship between two categorical variables. And the data set in front of me is a marketing data set from a Portuguese bank. They performed a survey on their customers, and they collected information such as their education, marital status, and so on. They know how much balance they have on the account, and then they gave them an offer for a specific kind of a savings account, and then they captured whether or not the people opened the account. So one of the things, it's easy to look at the relationship between numerical variables. It's not so easy to look at the relationship between categorical variables. And that's what I'd like to show you right now. So what I'll do another visualization. This one will be a scatter plot. And we'll look at a job versus education. Job. Education. Okay. And it's colored right now by this marital status, right? So in general, like the only color you see is the last points. There's tons of points behind the scene. So we'd like to get a general sense of distribution, and can look at it this way. So what I'll do is first of all kind of reduce the size of this marker, and now I'm going to jitter these points, right? So jittering is we're applying some random noise around the points. If you guys are familiar with a library called ggplot in R, it can do that as well in a static way. Here I'm doing it dynamically. So even after applying this, I sort of don't get a sense where most of the points lie. So I'm going to apply some transparency or an alpha blend to this viz, right? So now what I can start seeing is this pattern. First of all, I can see where most of the points lie, right? Where are the densities? So we have a ton of data on management here in the sort of this tertiary, what they call tertiary education, above secondary. We have a ton of blue collar and secondary education. But you can also sort of explore the relationship. And for instance, the student tends to be, we don't have as much data on it, but they tend to be single. It's colored in this green color. And the retired group here tends to be either married or divorced, and that's sounds about right. Right. So this is the kind of exploration we can do that is difficult to do with sort of a traditional plotting libraries, and it's quite easy if you can do this data jittering and application of transparency to the plot. So now I will go back to the PowerPoint. Okay. Just wanted to mention that there's a distribution called paranormal distribution that you see here. It's a lot skinnier, narrower than normal distribution, so it should be less risky in finance terms, but it's a lot scarier. So this is a conundrum of sorts that I think Greenspan was talking about. Moving on. So now I want to show you another exploration technique, which actually would involve us to fit quite a few models. And the reason I'm doing this is that same data set, same exchange data set, I want to now explore the correlation in these returns. I'd like to understand which pairs are very correlated and which pairs are uncorrelated and which pairs are negatively correlated. And this could help me in selecting, let's say, a portfolio set that I'm after. Also, while I'm going to do this, take a note of this particular ETF, which is called FAS. It's triple leveraged. What that means is that they advertise that they move for 1 percentage point in the financials, they would move up or so. I will also print the beta and the R-square on the graph. Maybe set the graph to have a little bit narrower line. Okay, so now we can see these betas in R-squared. R-squared is the strength of linear relationship. We'll see it's very high here at the top. So I'm going to sort it now by the correlation coefficient, R. So what I'll see is, okay, I can sort of quickly move through this line, right, and look and see what are some of the things that are super correlated, right? And you can see as I move down, the correlation kind of decreasing a little bit, right? Now, if I go all the way to the bottom, I should see negatively correlated pairs, right? So now the relationship is negative. And I do go somewhere to the middle, we should find things that are uncorrelated or weakly correlated. Right? Again, this could help in suggesting candidates for different portfolios. So what about that claim that was made by FAS? And we can evaluate it directly here. So here's the FAS versus XLF. So we'll click on that. XLF is the exchange-traded fund of financials that's non-leveraged. The FAS was the one that we talked about earlier that is leveraged. And the claim was that it was leveraged 3 times. Well, I printed the beta here at the bottom. And I don't know if you can see it's kind of small. But the beta is here is 2.65. And the scale of these returns are basically percentage scale. It's logarithmic returns, so it's basically in a percent scale. So it seems to be pretty accurate in their claim, right? I don't have the standard errors of this beta, but it'll probably be within a few standard errors. 3 will be somewhere in there. So it seems to be, in fact, going up 3 percentage points for every 1 change in XLF, and same thing on the downside, right? So not too bad. They're not lying to us, at least not about this. So with that, let me go back to the main event. So we looked at this kind of data exploration with some rudimentary model building. And so to bring back the progress that we just reviewed is the input data exploration. So I will now jump to the direct model exploration. So the direct model exploration, as I mentioned, is where we actually want to see sort of what the composition of coefficients, the composition of the errors of those coefficients, perhaps some other measures, although I tend to like the the size and error of model coefficients most, and look at different plots that can yield in evaluating those. And also look at things like residuals and QQ plots pretty quickly. And those indicate, especially in linear regression, how well the signal is separated from the noise. So with that, I'm going to introduce a third and final data set that we'll be exploring today. That data set is called wine quality data. This particular one has a sample of, I think, 1,000 or so wines, the red wines. And their quality metrics, there's quality rating, and then there's composition, right, of features which include things like acidity, chloride, composition, and so on. And what you can see from this plot, actually, it's already sort of the green points, which tend to be the lower quality ratings, tend to sit to the lower values of alcohol, and like 6s and 7s tend to be at a higher. So maybe people prefer their wine with a higher quality, higher amount of alcohol in it. So let me go now jump into this third set and really show you quickly how we build a linear regression. So here's the wine quality data. This particular method of building regression is actually another sort of off-the-menu regression builder. Another way of doing it for more complicated models is by hooking up R scripts, which I've also done here for other types of models. So there's that kind of flexibility. But let me do this one real quick. So that from the tools, we'll do linear regression. Choose regression modeling. And here I'm offered this choice of picking the response, which in our case will be quality, and the predictors, which will be everything else. I can add them to the model. I can also add predictors on a nonlinear scale. So I wanted to add alcohol as a quadratic predictor. I can do that as well. You can see it inserted this statement polynomial of second degree. So I'm not going to do that. Just get rid of it. And I will run the procedure. So it's just ran the regression. We got some output back. We see distribution of residual versus fitted. Looks like a mess, so I'm pretty happy with that. It should not have a whole lot of patterns in it. We can also look at this QQ plot. For those of you who are not familiar with that, it's a way of measuring how if residuals diverge too much from the normal distribution. It's one of the assumptions of linear regression. If they diverge a lot, the model may not be appropriate. So here, I'll show you how I can basically plot a line on top of this graph real quick. We do lines and curves. I'll add a curve, and the curve expression is just y equals x. So we just need to add that line. So you see the line's run through. It's not too bad. Yeah, I've seen a lot worse. So it's not a terrible fit, right? So now what I want to show you is the way of sort of looking at the model coefficient. So I put together this table, and what I did was I colored the coefficients in red if there were more than 2 standard deviations. The estimate was away more than 2 standard deviations. So the red things here tend to have less meaning, put it this way, than the blue things, right? So if you look at this table here, for instance, you see the intercept term is estimated at 9, but it's a huge standard error, so it's not very interesting. The density term here is large, but also has a very large standard error, so also not very interesting. But how do we, let's look at some of the things that are more interesting, and this we'll look at this chloride and sulfates coefficient. And this is where I think it's kind of cool to maybe ask some questions and see in this particular data set what's happening. So if you look at the chlorides, this estimate is, let's call it -2. So for what this is saying in essence is for 1 unit change in chloride, or 1 unit, let's say, increase in chloride, the quality units are decreased by 2, right, which is quite a bit. So, and that's assuming everything else staying equal. And that means, makes sense. People don't like to have chloride in their wine, or maybe it's not tasting very well. Interesting thing on sulfates, the sulfates, for every 1 unit increase in sulfates, the quality also goes up by 1. And then say, well, why would that be? Well, sulfates is a preservative, and perhaps what's going on here is that the wine that has more of this preservative tends not to spoil as much. So the more of it, the less spoiled wine, and maybe that's the reason behind this correlation. So I guess the point here, the general point, is that try to ask questions like this of the model itself, and not be just concerned with predictive accuracy, which we will get into, to kind of understand what are some of the contributing factors to the model. Okay. So one of the things that I mentioned that are kind of interesting is, well, I showed you sort of one way of looking at this model, one way in which I fit the model, but what about iteration, right? So where's the model iteration part of this? And so, I'll show you quickly how we can iterate this model with the application, and maybe perhaps get to a better model, get to a more parsimonious model. And the method I'll use is a well-known method. It's been invented by Hirotugu Akaiki. I'm sure I'm messing up the pronunciation, but it's based on the Akaiki information criterion, and it's a method that maximizes, tries to find the most likely model under the data with the least amount of parameters. So it penalizes penalizes model complexity. And so if I go back into the application, I'll show you the output. After we applied this stepwise ASC procedure, and point out a couple of things that are of interest. So first of all, after we apply this procedure, we'll look at the coefficient table. We see that the intercept now has small errors. We don't have density. If you recall, density has huge errors. So those are iteratively removed from the model. So the model is smaller, and the errors are now sort of reasonable, right? And I also wanted to show another sort of visual, which some of you may recognize if you work in R. On the left-hand side is a plot from the ARM package of regression estimates. This is a coefficient plot. I like this particular plot very much. And the way it ended up here is it was sort of we can wire up the R script and pass an arbitrary image from R displayed here. So in this particular plot, you can see a little bit better, perhaps, that the coefficients are away from 0. So we plot the coefficient value, and then the error bars, like 1 and 2 standard errors, and we can kind of quickly see, those coefficients tend to be larger, and also the ones that tend to have smaller errors. And so this is sort of one of the way we would iterate through a model, and obviously we could hook up a lot of other methods to this as well. Okay. Back to this presentation. So we now covered this input data exploration. I talked a bit about direct model exploration. And so now I want to talk a little bit about model performance. And here the focus is going to be the ROC curves, and hopefully if we have some time we'll do some simulations. So I'm not sure how many people have heard of these curves, so I will tell you briefly about them, not a whole lot, and sort of explain explain how they work, and then I'll show you inside of the Spotfire app an example of using them to compare performance of classifiers. So how do we look at these ROC curves in evaluating classifier performance? We first of all always do it on out-of-sample data, and keep in mind that the output of the model is a probability. And also the fact that the accuracy metric may not be the best metric for evaluating a model. And that is because, say in a fraud detection case where, we may only have 1% fraud, so the naive model can set all the data to no fraud, right, and it will be 99% accurate, but perhaps not a very good model. So what we do is instead we generate this kind of matrix, the lower left here, we call it a confusion matrix, that breaks our guesses and actual outcomes in these cells that correspond to this true positives, false negatives, and true negatives. And what we plot is we plot this curve of a false positive rate, and a false positive rate is simply, hey, we said it's fraud, but actually it's not. That's the false positive rate, or we said it's cancer, but it's benign, and against the true positive rate, right? And you can see sort of in this framework, it's always sort of a tug of war between the true positive and false positive. We'd like to get these curves as close to the top as possible and be somewhere in this area. So the more area under the curve that's captured, the better, in essence, we do. So I'm not going to, dig too deep into this, but the way we generate this actual curve, if you were to program it, is by generating many of these confusion matrices for different values of the probability cutoff. So with that, let me go back to that data set that I showed you before, which was the bank marketing data set, and show you an output of a procedure like this. Okay. So here's this data. Some of the parameters that we can configure. Here, the parameter configuration, by the way, in this tool is fairly simple. You just drop it on from the canvas, and then you map it to some document property or to a script. So in this particular case, I'm saying, size of the training set. Now we're going to evaluate the performance on the test set, right? We always want to do add a sample, as I mentioned before. We can either scale data or not. It's a good idea to scale. And then we can choose and fit several different models, right? So here I wired the standard GLM that you could be maybe familiar in R and the elastic net. And so if I actually run these, right? Let me get a curve, these curves like this. So let me just get rid of that. So here's what you see, and I hope these are coming through okay, are three different ROC curves that are plotted on top of each other, and they're done for these three types of models for elastic-net GLM test and GLM train. What you'll notice is that show you another time series data set. The idea of the simulation is we want to kind of understand how well did the data, did our model capture the underlying process. And the procedure for that is fairly simple. We're fitting a model, we're simulating from that model, and we compare it to real data. And here we have to kind of be careful not to confuse noise with reality, and sort of to demonstrate the point, if you look at this graph of two sets of asset prices, can you tell from just looking at it which one is real and which one is fake? If you're looking at it, you know, long enough, I mean, I don't know, I can't tell the difference. In fact, the top one is the Euro USD exchange rate, and the bottom one is the cumulative white noise that can be generated with this really, really simple model. This noise equals cumulative sum of normal variables, right? So it's the point is it's so easy to get fooled by randomness if we don't know what we're looking at. Now, if we look at the percent changes, this is the same process only in this daily changes space. You kind of see that they're kind of not the same, right? The noise process has sort of more of these spikes than it's, you know, this one, the acid one is a little narrower and so on. So you basically can tell from this plot a little bit better that they're really not the same thing. So, but when we fit the model to it, right? So now this is the final plot from when we actually fit the ARIMA model to the Euro USD and simulate it. So bottom is simulation from the same model. It kind of looks similar. It looks like it captured the underlying data process. And this is the kind of thing that that I'd like to see. And just to give you a very brief sort of demonstration of how it would work in Spotfire, here we'll have back to our original data set, and I have this ARIMA modeling application that I built. I can pick one security, let's say it's a SPY. We can see the prices here. I can quickly select a subset that I'd like to model, and then we're just update it. And so, and do a simulation fast. Okay, so simulation just completed. We actually have a forecast and we have simulated data. If you compare this simulated data at the bottom, this under fitted ARIMA, and the actual real data in this diagram that says log returns with 2 ASD bands, they don't kind of look the same. So this is an indication, a very clear indication that the model, the simple ARIMA model, did not capture the process well. And in fact, the confirmation of that is this plot at the bottom. This is what we call Garch effect in time series, and basically indicates that there's this volatility clustering that goes on. So just by running the simulation, I can be fairly certain that the simple ARIMA model is not sufficient. So I'm going to have to do some more modeling, perhaps modeling it as the Garch process. Okay, so I'm almost done. I mentioned that one of the things that we try to do is we try not to sort of over-optimize or not have a separate process for optimizing the code. And this is where we work very closely with R. Some of these models that you've seen are written in R, and they're baked directly into Spotfire. And it is done through our own R engine that was pretty much developed from scratch to improve performance of core R. And so I want to show you just a quick performance comparison. So this is a model fitting exercise, about 5 million rows. Here's the code. It's basically a type of maybe like a fraud model. This is the Y's are zeros or ones. And to fit that model in under open source R, here you see 107 seconds. Under TERR, which is TIBCO Enterprise runtime for R, 17 seconds, right? So a little bit over 6 times faster. For the model scoring, 20 million rows. Here's the generation new data, 84 seconds for open source R, and 1 second under TERR. So quite a bit of performance in performance improvement, especially in the model scoring. And so it's pretty easy to put this kind of code in production. There's no need for sort of specialized environment. So as a summary, we covered this loop from plot relationships fitting a model. Luke talked about the input data exploration. I talked about the direct model exploration and talked about some of this performance evaluations. And there, the important point, I think, was that we want to, if we want to understand the composition of the model, if we want to understand why it's doing certain things, it is instructive to look inside under the hood. And if we're only interested in predictive, then perhaps the things like ROC curves and other model performance are appropriate. And my claim is that we can be more productive if we do this in an iterative fashion, as I demonstrated to you today. So with that, I'd like to thank you very much for listening. Feel free to contact me, like at TIBCO.com, or check me out on Twitter at Eric Novick. Thank you very much.
Thank you so much, Eric. That was a great presentation. We do have some questions that came in during the presentation, so I'm going to pull this back to my slide here. During, oops, I beg your pardon. Hold on 1 second. There we go. So the questions, while I'm asking the questions from the audience, Eric's information is listed there. So please take it down. If you want to reach out to Eric after the presentation, please feel free to do so. So Eric, one of the questions that came in was, how well can Spotfire handle large data sets?
Yeah, that's a great question. So two things. So one is you saw, like, when we're talking about sort of millions of rows, we can work with that really well in memory on the client, and it's a fairly optimized engine for doing sort of the scale of millions. Billions of rows, we have partnership, close partnership with Teradata and Teradata Astra. We have direct in-database connectors to them, and those guys scale out to Hadoop scale, right? So billions of rows through the Teradata connector.
Okay, very good. Another question is, how can you deploy these models in a real-time transactional environment?
So yeah, one thing I did not go into is deployment of the production. It's sort of in a real-time production environment, which is a talk in and of itself. But basically, there's one way now to do this. We can take the model coefficients and export it to TIBCO Business Events, which is runs on TIBCO infrastructure. For those of you who are familiar with that, we've also recently acquired a company called Streambase that does extremely high volume transaction processing that takes these models and injects them directly into things like real-time execution systems for banks. So we're kind of excited about that, and we'll be doing a lot of integration work with Streambase.
Oh, very good. Another member of the audience was asking, do you have any rule of thumb about the time spent trying to establish a model covering most of the data versus time spent on outliers / 3 sigma deviates?
So that it's kind of difficult to say. Obviously it depends on the complexity of the problem and amount of data and so on. I mean, in my own experience, I've seen productivity improvements in 5 to 10x once we have the platform up and running. So it's maybe a little vague, but if there's a specific type of data or size of data that's of interest to the individual, I encourage you to send me an email, and I'll dig up some more specific answers.
Okay, I think we have. I'm going to go to one more question, and then we'll wrap things up here. Can the same product and interface be used by statistically uniformed users and business analysts? Okay,
so yeah, for people who are sort of not statisticians, and so this is where I think it's kind of a cool tool, because what I sort of showed you are some of the modeling capabilities. The same platform we use to build interactive dashboards for end users who don't have experience with stats. If you can imagine, I can build a predictive model, I can deploy it out on a network, and then power an end user visualization, right, that generates maybe forecasts or classification from the interface itself. So the platform is sort of meant to address both, and it's, I think, one of the cool things about it.
Very good. Okay. Well, Eric, thanks so much again. I want to thank the audience as well for helping me when we were having a little bit of trouble there. At least I was. A couple of quick announcements. So please mark your calendars for July 9th and our next Data Science Central webinar, Big Data Science, sponsored by Pivotal. As I mentioned earlier, this event is being taped, so if you want to review it, it will be available on the homepage of Data Science Central on the video section in the next day or two. So this brings our webinar to a close. I'd like to thank our audience again for their attendance. Thank you for the questions. Thank you for the feedback. Eric, thanks for a wonderful presentation, and certainly appreciate the laced in humor there as well, and some great perspective. And thank you also to TIBCO Spotfire for sponsoring today's event. My name is Tim Madison. Yeah, my pleasure. My name is Tim Madison. I'm very pleased to have been the host today, and I will look forward to seeing you all again July 9th. Take care.